My name is Lukas. I'm a founder and the CEO of TACEO. And today I want to talk to you about this upcoming primitive called collaborative SNARKs and why it enables verifiable encrypted compute, and also how we made collaborative SNARKs accessible for every CK developer so far. Now, the next slide is usually, I think I don't need it in this track, like it's basically a justification why conventional compute is the one key thing that will unlock the commercial viability of blockchains. So we can directly dive into the topic of coSNARKs, and I want to do a quick temperature check. How many of you are familiar with collaborative SNARKs? It's getting more and more, probably also because there were two big announcements in this week, like two companies independently made private verifiable ML compute possible. I think Makara is sitting here, so Hashcloak, big shout out to them. They, for at least what I know, made the first private verifiable ML training so far, and they did it with coSNARKs. Now, before we jump into what coSNARKs are, I want to motivate why they are important. And I already mentioned that it is about encrypted verifiable compute, but I think why they are so particular interesting in the blockchain ecosystem, we'll see if we look at the state models. So we have basically two state models so far in blockchain, and the first one arrived right 2015. Like when Ethereum launched, we get this programmable blockchain and it gave us public state. And the great thing about public state was it was by default composable. And a lot of people don't think about it anymore, that this is one of the key properties why we have these great network effects in public blockchains. Because you can build upon each other. You can build it on other smart contracts, you can call them, and their essential feature is that they are composable. Now, of course, the big drawback is that everything is public, and this hinders a lot of institutional adoption and is also really bad for privacy. So if you kind of more in the idealistic way of Web3 and to want to push forward of then create a new internet, if we get blockchains without privacy and they're becoming huge, I would be even more afraid than we are now in Web2. And thanks to very talented and brave teams that kind of not jumped on the scalability path of CK, but built something different. They built these programmable private blockchains like Aztec, Alio, and recently also Maiden. And what they achieved is they gave us private state. But unfortunately, private state is not by default composable. So we have to work harder to make it composable and to achieve these network effects that we're seeing on these public blockchains. Now, what is the exact problem and how do we achieve composability? So first, we want to maintain the verifiability for the state. And second, we want to be able to compute on multiple parties' private inputs or private states in the sense of blockchains without leaking them to anybody. Like I think we have heard this in the talk extremely well already. So how do we solve this? Verifiability, I think everybody immediately jumps to CK. And the second one is a textbook example of the definition of secure multi-party computation, or short MPC. Now, and that's exactly what collaborative SNARKs are. It's CK plus MPC. Before we dive into how they are constructed, let's briefly review what applications are enabled by collaborative SNARKs. Like the lowest hanging fruit, and where the paper, which we see later, focused a lot of, is private proof delegation. So if your device is constrained and you cannot run the proof in the time that you want to finish it, you can now outsource the proof generation in a private way to an MPC network, and you kind of get server-side CK proving capabilities without losing your privacy. The more evolved use cases are around private shared state, so this composability of the private state, which we see example in private dark pools. For example, Renegade is one protocol that is live with coSNARKs on Arbitrum using this for their private dark pool. And then we have other examples, like I mentioned, the private CKML, or on-chain games with asymmetric information symmetry. think of fog of war, for example. Now a bit back to the theory of collaborative SNARKs. Like, there's this paper in 2021 from Dan Bonnet and back then his PhD student Alex, where they showed how to combine MPC and CK. Now, just combining these two technologies might end up being a good blog post, but why was it a paper even, and why it's a very significant paper? Like, they showed how you can run, like how you collaboratively compute a proof in a very efficient way. Like, instinctively, if you think like combining two of these rather advanced cryptography subfields, MPC and CK, both with each of their overhead, you would maybe think that you're getting the overhead of MPC times the overhead of CK, and then it really blows up into your face, and it's not really practical. But they could show that it can be combined in such a way that you have little overhead among the CK computation if you add MPC. So basically, you kind of can add MPC for free. And they really had a bold statement in there. So depending on a rather good network connection, you can basically compute every proof that you can compute in the single proof setting, you can also prove in the collaborative setting with little to no overhead. This is quite a strong statement. Now, that's where our journey started. Like, we want to make this programmable, this coSNARKs programmable and available to other developers. Roughly 1 year ago, we kind of laid out the design at the CK Summit 11, and then started to implement it. First, we started out with Circum, and so there is now a library out there that's called coCircum, which allows you to run any Circum circuit in this collaborative fashion. To get a better developer experience, we then started around the summer to develop coNoir. And for those of you who don't know, Noir is a CK domain-specific language that's heavily leveraged and developed by the Aztec ecosystem. It has a Rust-like syntax, so much nicer than Circum. Now, what is needed, and what is coNoir, and what is needed, like, what did we develop to make coNoir possible? First off, like, it consists of two components. It is a multi-party computation VM, plus MPC proving backend for Noir. So Noir is like highly modular, so it allows you to use different proving backends. And in our case, let's start with the proving backend. UltraHonk is one of their popular CK proving systems. We MPC-fied their proving system, so re-implementing UltraHonk in an MPC environment. Like, for those of you who are interested, the developer doesn't have to know this, but like, the hard part in implementing a proof system in MPC is always when you hit up nonlinear functions. So the linear functions are pretty fine, they are extremely fast, and they're also easy to implement, like the MSMs, for example. It gets tricky when nonlinear operations come into play, and here, for example, with the subject protocol in the specific UltraHonk prover, this is the most complex part. The nice part of collaborative SNARKs is that the verification, the verifier is exactly the same as the traditional verifier. So you don't have to build any infrastructure for this. You can leverage every verifier that is out there. And the second part is the even more complex part, which is not touched upon in the paper. It is the witness extension. Usually part of the zero knowledge proof generation that is neglected or not paid too much attention, because it's less heavyweight and you don't focus in the CK native space a lot on it. But and you don't need it for private proof delegation. That's why also it was neglected in the paper. But if you want to compute in private shared state, it's essential that you have also the witness extension in a confidential way. And that's why we ended up building an MPC VM for this witness extension, because this is like basically a witness extension in the CK space is basically a program execution in plain. Now, as Noir allows arbitrary programs, you also have to allow arbitrary operations, and you end up building a general purpose tooling for MPC. Now, I think we have a bit time to look a bit at the deployment of Noir, or the developer experience. So on the left lower side, you see a Noir program. It's like the same syntax that you used from Noir. Here it's a Merkle tree inclusion proof, and like it gets compiled down with Noir, but then differently interpreted with our tooling, with our MPC VM, and differently executed with our proving backend. And client side, you see like Bob and Alice want to collaboratively compute this inclusion proof. They do secret share their data, like a technique of MPC, maybe we get into that later, and directly secret share this to the MPC network. That's the only thing they have to do. So this is a very lightweight computation. They can even do this in the browser. And then the proof gets computed, and you can then send the proof wherever you want. Here it's abstractly called Charlie, but it could be a smart contract where verifier sits, takes the output, and verifies the proof. Now, this is all good, but how is the performance now really of collaborative SNARKs? And in this case, Noir, coNoir. Like, this is an unoptimized implementation. We'll start now to focus on performance. But this kind of gives you at least some idea. And I think like the absolute numbers are quite okay. Like you can do a Poseidon 2 hash function in 100 milliseconds, for example. You can do an inclusion proof of, with a size of, the tree of a size of 16 in 1 second. But if you look at like the overhead from the MPC proving, so the collaborative proving to on the right, the two columns on the right are just CK only, then you see there's still quite an overhead. And this is mainly due to engineering. So there's not really a lot of theoretical boundary that we cannot achieve like the same performance as CK only. And we have seen this by implementing coSNARKs, where we kind of are reaching between rapid SNARKs and SNARK-GS performance. So we would expect to go this number go down over the next months closer to the right side. Yeah, as I said, like our plan for the coming months is performance, 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 and like this are general performance improvements, but also like Noir has these features of black box functions, which if you're kind of thinking about VM, this is more like a precompiled stuff. I hope you had a quick intro to coSNARKs, what they are and why they're becoming popular. If you want to like try experiment it with it, here is the GitHub. If you just want to kind of collaborate, research, please reach out to us. Everything is open source and happy to build with you.